Welcome to our series of lectures on Higgs mechanism. Today we are going to discuss about nuclear structure, bit of nuclear structure, and what about the fields. And if time permits, we will do some mathematics also. But to start with, okay, the simple pendulum. Sorry. A simple atom consists of a nucleus having neutrons and protons. This all we know that a nucleus consists of a neutron and a proton. An atom, there is an electron here. This is the nucleus, which consists of neutrons and protons. And electrons are bound to the nucleus with electromagnetic force. This makes atom of the chemical element. But neutrons and protons swap their states. Neutron converts into proton plus electron plus a particle called neutrino, antineutrino. Now, what force which binds these neutrons inside the nucleus? So the force, what force binds protons inside the nucleus? Of course, it must be very short, in very shorter range, and must be very strong, so that it does not, so that it could overcome the electromagnetic force. Because in the nucleus we have protons also. Protons may repel, but the force which binds these neutrons inside the nucleus must be stronger, so as to overcome this electromagnetic force. And also it must be very short-ranged, so that its effect, so that's why we don't feel its effect outside the nucleus. It's only inside the nucleus. And the range of that strong force is 10 power minus 13 centimeter. That is within the region, within the diameter of the nucleus. The only force which we experience in our daily life, other than gravity, is electromagnetic force. Whatever force which we perceive in our daily life. The force by which I am holding this chalk, and the force by which this this chalk dust is attracted to this blackboard is also due to the electromagnetic force. Or whatever the force if you think, all ever except gravity is all electromagnetic. But there are two forces inside the nucleus. One which is just written strong force, and there is another force which is called weak nuclear force. So we have all four types of forces. So the types of forces strength of the force, and theory associated to that force, and the mediators. So the force which is inside the nucleus, one of the force which is the nucleus is called strong nuclear. Then the next force in strength is electromagnetic, and then we have weak force which is also inside the nucleus, weak nuclear force, and last one is gravitation. gravitational force. So the strong, if we rate this as 10, then this must be 100 times less than, and this is 10 to the power minus 11, and this is 10 to the power minus 42. And this strong nuclear force, the theory associated is called chromodynamics. And this is called as electrodynamics. And the weak nuclear force is called, theory associated is called flavor dynamics. And this one is called geometrodynamics. And according to field theory, these interactions is due to kind of particle which acts as a mediators. As for example, two positive charge repel each other because they form a field. This charge has formed a field, electrostatic field, this is also electrostatic field. And the quanta of that electrostatic field is called photon. So the photon is responsible, is a mediator in between the two charges for the interaction. So the mediators here for the strong nuclear force is called gluons. And the electromagnetic is called photons. For the weak nuclear force, we have W plus minus and Z. And the geometric dynamics it's not yet invented or discovered, whatever it is, but its name is posed as gravitons. Not yet discovered. So photons have no mass, has no charge. Gluons has charge. And this weak nuclear force is mediated by three types of particles. These are called gauge bosons also. So these three gauge bosons, W plus, W minus, these are charged one and these are uncharged. Now, particles inside the nucleus, we have not only the neutrons and protons inside the nucleus, but there are particles which are categorized as baryons and mesons. So the nucleons inside the nucleus. When inside the nucleus there is not only neutrons and protons, but we have a large number of particles. Some are called baryons, others are called mesons, depending upon their masses. Usually and and then we have an electron which is outside. So these baryons and mesons are not elementary particles. They are composite particles. Baryons are made of, and the elementary particles, they are made up of quarks. The baryons are made up of 3 quarks, mesons are made up of 2 quarks, one a quark and an anti-quark. And the quarks, we have 6 quarks, and the 6 quarks are up, down, charge, strange, top, bottom. So these are the elementary particles which forms baryons and mesons. Now these, suppose this is a proton. The proton is made up of 3 quarks. These are 3 quarks. Proton is made up of up and down, 2 up and 1 down. And neutron is made up of 1 up and 2 down quarks. So, and there is another, here say it is neutron. This is 1 up and 2 down. Let's say, make it downs. This is downs. This is 2 up and 1 down. So this is proton and this is a neutron. These quarks are the force within these quarks and force within this proton and neutron are all mediated by a quanta called gluon. The gluon here also and here also gluons. And this electron, which is attracted to the nucleus by a particle that's called photons. The attraction between nucleus and electron is mediated by a particle, field quanta, that's called photons. Okay, and we have this. Now, according to standard model, according to we have a set of we have a up, down, and charge, strange, top, bottom. We have 6 quarks. This is the first generation of quarks. First generation. This is the second generation. And this is the third generation. We have electrons and a neutrino corresponding to this electron. And the heavier version of the electron we have called muon, and its corresponding neutrino called muon neutrino. And then we have still have tau or tau neutrino. And these are called, these are quarks. And these are leptons. But all of them follow the Fermi-Dirac principle because all of them has spin 1/2. So they are all called fermions. All of them, quarks as well as leptons, are called fermions. Quarks and leptons. All of them are fermions because they follow the Fermi-Dirac statistics. And now we have second, these are called mediators part, which took part in the interaction. These are called gluons, photons, Z and W plus minus for weak nuclear forces. And there is one more, is called Higgs particle. Now these all these are bosons because they have spin, integral number of spins. So these are called gauge bosons. Gauge bosons. Their spin is 1, and here the fermions have spin 1/2. And there is a scalar field here, which is called Higgs field. Which is a scalar field, and spin is 0. Now, the next topic, that is what is field. The next question that arises in our mind is what is field? Okay. So then what is field? Field of any physical quantity is a function of position and time. If for every position and time we have certain value of a physical quantity, we say that we have the field of that physical quantity. Now fields can be of two types. This scalar field and vector field. As for example, potential field. Potential field, gravitational potential field, electrostatic potential field, whatever field. This is a field of energy. It does not require any direction. So this is a scalar field. Now we can say that we have a temperature field. We have a hot body here, and it's there. It creates a temperature around it. We have for every point we will get certain temperature. We can say that this hot body creates a temperature field. So we have a temperature field. Temperature field. Now we can have a field of light intensity, because this bulb has created intensity in this room. So we have light intensity field. All these are examples of scalar field. Vector field, we have electrostatic field. Field, this is the force experienced by test charge. So this is the force field. So this is a vector, force is a vector quantity. So such. Gravitational field is also a force field. And so on. So we can divide fields into two categories. One scalar field and vector field. Now, what about quantum field? According to quantum field theory, every particle is associated with a field. Fields exist everywhere, even in vacuum. We cannot see or detect it by any means. Lagrangian associated with the fields are denoted as Lagrangian density. We have discussed the Lagrangian density. Now the question that pops in our mind is that what kind of fields are we talking about? What kind of Lagrangian are we talking about for a field? How can a field have potential energy and how can a field have kinetic energy? Now, according to, we have three types of fields. According to standard model, we have three types of field. One is called fermion fields. That's field created by Fermi particles. Fermi particles, the particles which have spin 1/2. So these are called fermion fields. Now, two is bosons field. Fields that is created by particles which follow Bose-Einstein statistics or having spin 1. These are having spin 1/2. This is a fermion field, boson field. Now we have scalar fields also. Fields which have spin 0 particles. We have seen that according to our standard model, we have three types of particles. Fermions, spin 1/2 particles, spin 1 particle, spin 0 field particles. So the particles which have spin 0 are called, the fields generated by those particles are called scalar fields and the boson fields. But this is an example, scalar field. This is Higgs field. So Higgs comes here for the first time. Now the Lagrangian density which is the difference of kinetic energy and potential energy per unit volume. So it is difference of kinetic energy and potential density. Now the question that arises in our mind that how field have potential energy. So this we can understood by, suppose we have a very simple answer to this is that in elementary physics we know that parallel plate capacitor we have electric field and the work done taking unit charge from this negative plate to positive plate is the energy which is stored, and this energy is stored, that is called potential energy, and the So the capacity of this plate, capacitor plate is A epsilon naught by D, where A is the area of this plate, epsilon naught is the permittivity of the vacuum, and D is the separation between the plates. So the capacity is given by this formula, and we know that the potential energy stored is half C V square. V is the potential in between the plates, and we also know that this is related to electric field B by D. So if you substitute here, you will get half C E square D square. And if you write this, substitute the value of C here on here, you will get half A epsilon naught by D square. This is the potential energy within the plates. Now, if you want to find the potential energy density, energy density is divided by volume. The volume of this field area is area times its separation. So it will be half A epsilon naught by D E square by D square divided by volume. So if you divide this and you work out, you will get half epsilon naught. So it means the potential energy density of this electric field is potential energy density is proportional to. Similarly, we can, for any field, say phi, for any field which is for any phi field, the potential energy density associated will be proportional to phi square. So now we obtained what is the meaning of potential energy density of the fields, because it's related to the square of that field. Now, what about kinetic energy? For kinetic energy for a particle of mass m having velocity v is given by half mv square, where v is the variation of the position with time. Now, similarly, the kinetic energy for the field will be kinetic energy for the field. Now, the field varies not only with time, but it also varies with position. So the kinetic energy for the field, here the kinetic energy is proportional to the square of its position, variation of position with time. Similarly, the kinetic energy for the field must be variation of field with square the variation of field with time. Also, it's variation with positions. Now, this is del phi by del square, del phi by del y square, del phi by del z square. Now, this minus sign comes because we are dealing with the 4 dimension. And from Einstein we know that any S, any interval is c square t square minus x square minus y square. That's why these are. Okay, so these are all about. Now this is written in a very compact form as del mu phi del mu phi. So where mu runs from 0, 1, 2, 4. So the next class we will discuss why I am writing this as one superscript and one subscript, and not, we could have written as like this also, 5 whole square. For 0 it's this is del mu phi means del phi by del x mu, and mu has 4 components, and 0th component means time component. First component means x component, then this y component, this. Had we written this like, it would be like del phi by del x mu. It means del phi by del t, square of del phi by del t, plus the square of del phi by del x. But here it's a minus sign. That's why it is written like this. So in the next class we will discuss why I am writing it like this. Okay. So we will do these methods we will do in the next class. Okay.